It sounds crazy, but a single miscalculated drop of chemical in your lab, it can literally bring down a massive industrial cooling tower. Welcome to this explainer. Today, we're standardizing our water treatment reporting to stop these catastrophic failures before they start. We are here to ensure every single piece of data tells a logically sound story.
Because, look, a miscalculated drop of reagent, or a meter that's read wrong, doesn't just make your report look messy. It leads straight to undetected scaling. We're talking massive energy waste and complete equipment failure. This catastrophic breakdown is exactly what's at stake when laboratory protocols fail.
So, I want you to really think about this for a second. What happens to your facility when your lab data lies? If the numbers you write down are mathematically impossible, how on earth can we trust the health of the cooling system we're supposed to be protecting? Spoiler alert, we can't.
So here's how we are breaking down the anatomy of a perfect report today. 1. The cost of an error. 2. Measuring TDS and pH. 3. Titration for hardness and alkalinities. 4. Report structure. 5. Validation rules. And 6. 3 key takeaways.
All right, part 1, the cost of an error. Let's talk about the high stakes of industrial water testing.
Moving right along to part 2, measuring SDT and pH. We're looking at precision with the portable combo meter.
Okay, so our entire testing protocol basically has a mathematical ceiling. I'm only going to define these once, so lock this in. SDT, or total dissolved solids, is the absolute maximum concentration of all dissolved substances in your water sample. This one number dictates the physical ceiling for every other measurement in your report. Make sense? Meanwhile, pH is simply the measure of hydronium potential, or basically how acidic the water is.
To get these foundational readings, you're going to use the portable HANA Combo Meter. It's a fantastic piece of hardware. You'll just carefully toggle between the measurement parameters to get exactly the readings you need.
But here is a massive common lab error we see all the time. Did you report the direct PPT value straight from the meter? If you're writing down a PPT reading exactly as it pops up on that screen without converting it, you are instantly invalidating your entire log.
So, to avoid that, you've got to follow the HANA Combo Meter golden rules. First, you absolutely must multiply your PPT results by 1,000, period. However, your ppm and your pH results, those are logged exactly as the device displays them. Do not mix those up.
Okay, part 3, titration for hardness and alkalinities. We're visualizing precise chemical reactions here.
When it comes to hardness, the procedure is strict and it is uncompromising. Step 1, add exactly 10 drops of ammoniacal buffer and mix it up. Step 2, add 10 drops of iriochrome black and mix again. From there, we are watching closely for a critical color change to figure out if we actually need to start titrating with our EDTA reagent.
Now, watch the chemical reaction. If your sample turns bright blue right away, great. Your hardness is perfectly at 0 parts per million. You stop right there. But if it turns purple or pink, you have to titrate with EDTA, drop by drop, until you hit that exact blue color.
Time for another quick logic check. Are you multiplying your spent milliliters by 40 or by 200? Using the wrong multiplier for your sample volume is another huge trap. Look, a 25 milliliter sample means you multiply the spent EDTA by 40. But if you're using a 5 milliliter sample, that strictly requires a multiplier of 200. Always check your volumes.
Now for alkalinity. This specific matrix dictates exactly how you calculate your hydroxides, carbonates, and bicarbonates. It's completely based on the relationship between your phenolphthalein result, which we call P, and your methyl orange result known as T. Honestly, just follow this table and the math basically does itself. Moving to part 4, report structure. Let's talk about building a logical and chronological data log.
The anatomy of our report format is rigidly standardized into 6 key parts. It flows from the equipment type and client name, through the sequence list and monthly dates, all the way down to the monitored parameters and descending analysis results. Keep in mind, those parameters will actually change depending on the specific control ranges of the equipment you're testing.
Let's pause right here and apply a little common sense to our logs. Ask yourself, is it logically possible for your feeding water to have higher dissolved solids than your cooling equipment? The answer is a hard no. Your feeding water can literally never have a higher value than the equipment itself, simply because only reverse osmosis systems can actually eliminate total dissolved solids.
Which brings us to part 5, validation rules. These are the absolute laws of logically sound data.
See how all this builds on those definitions we went over earlier? Your total dissolved solids, your SDT, will absolutely always be your maximum value. Total alkalinity and total hardness are merely components of that SDT, right? So logically, mathematically, they can never exceed it in a correct log.
Furthermore, your pH and your alkalinity have to logically agree. Remember, this is chemistry, not guesswork. If your alkalinity is 0, that dictates a pH no higher than 7.9. Conversely, if your alkalinity is 4 or higher, that strictly requires a pH of at least 8.0.
All right, let's wrap this up with part 6, 3 key takeaways. The final rules for perfect laboratory analysis.
Remember these 3 pillars. Number 1, SDT is always the absolute maximum value in your report. It is your ceiling. Number 2, always multiply those combo meter PBT readings by 1,000. And number 3, pH and alkalinity must strictly follow the chemical logic rules we just talked about.
Because ultimately, the immense responsibility of an entire industrial cooling system rests on a very simple question. Are you just writing down numbers, or are you telling the true story of the water? At the end of the day, it all comes down to whether you respect the logic inside a single drop of reagent.